Hello, this is going to be the video where we talk about, we're going to review TCP/IP devices. It's kind of a precursor for Networks 3 where we're going to talk about Cisco equipment and configuring network devices. So it'd be kind of nice to know how networks work. So let's get started. Let me pause real quick and shut my door. Hold on. Okay, we're back. So this is going to be under lessons, precursor topic TCP/IP review. Also, I do have a step-by-step guide here and a walkthrough of installing GNS3 and GNS3 VM, both of which you need to do in order to do the practices. We're gonna. These are the slides. Anyway, go back to the precursor. Here's the TCP/IP. Here are the slides. The desktop presentation will be right here. It's currently hidden from you. I can hit the preview mode to say, see, I told you so. Precursor topic, see, I told you so. It will be down here, and I'm playing with direct YouTube linking just for fun. All right, but this is the presentation we're going to do, so let's get started. There's a lot to cover. As a matter of fact, too much to cover. I'm going to go way too fast, but you should have had this already, so this is meant as a review. So we have network models. This helps us understand the network. Again, we have the 7-layer OSI network model, the granddaddy of all network models. We have from the top layer, we have to the bottom layer, we have application, presentation, session, transport, network, data link, LLC, MAC, and physical. So going from the bottom here, all right, we have physical. That's the actual physical network. Those are the electronic signals on a wire or electromagnetic waves in the air if it's a wireless network, right? Data link is going to have LLC, which is short for logical link control. That's going to control putting the data either in the air or on the wire. We have the MAC, which, logical link control does the actual, logical stuff, the actual dividing up into frames, the hash values, that kind of thing. MAC actually puts that in the air on the wire. Media access control is what it's short for. Most famously, we have the 48-bit address, MAC address that's in there. The network layer is a logical layer that handles the routing, so it's able to move traffic, the packets at that layer from here in Springfield up to the Space Center, if so need be. Okay, we have the transport layer. That's going to be responsible for port. We have IP addresses that's on the network layer. We have port numbers on the transport layer. That's layer 4. It's going to divide up traffic again into not sections. I want to say sections. It's not right. That's sessions. Segments. Yes, segments. It's going to divide them up into segments. Again, do another hash value to make sure it works. That's what transport's for. That's layer 4. This is kind of the realm of the. Let's turn on the pointer. There we go. That's better. This is the realm of the network administrator. The session, presentation, applications, kind of the operating system. Okay, this is the session is going to allow information moving from one operating system to another operating system. Presentation is going to allow is going to encode data. Might do some encryption. Although encryption often takes place in these layers as well, but it's going to encode the data, and applications what the actual user is going to see. All right, so we have the DoD model, which is process, which is layers 5, 6, and 7. Notice this is going to be a trend, right? We're going to take 5, 6, and 7 and say that's help desk problem. That's not us network engineers problem. And the DoD model they call it host to host is layer 4, or transport still works best here at TCP/IP. We have internet at layer 3 because again this is what lets traffic move around the WAN. Down here we just call it network. Although some people do like calling it internet. And then we have network interface, which is 1 and 2. Now in the DoD model, they call it network, which I think is just network interface is probably the better one. NIC that operates at layer 1 and 2, right? It's going to take that data, cut it up in pieces, do some calculations on it, use the MAC address to get it on the wire and move it on to the next node, right? Network interface. Okay, we I kind of went through this again. Layer 1, we're gonna have standards here, right? Cat6, wireless frequencies. We could have collisions here if we send data on the wire at the same time. That's a problem. Layer 2, we're gonna have carrier sends media access collision detection or collision avoidance. If it's wireless, it's collision avoidance. It's more aggressive because collisions are more apt to happen. Though that's part of the MAC to make sure that we don't send traffic on the wire at the same time and get a collision. So layer 2 helps prevent collisions. What happened at layer 1? We communicate via MAC addresses, which are 48-bit hexadecimal addresses. So there's going to be 4 divided into 48 is 12. There's going to be 12 hexadecimal numbers and letters. ARP characters. ARP is the protocol, address resolution protocol, that given a IP address, it's going to get a MAC address, right? So us stupid users only know IP addresses. We don't measure MAC, and we don't memorize MAC addresses. But at layer 2, we need a MAC address to communicate. If we're going to go station to station at layer 2, we need a MAC address. So ARP will sit there and say, okay, stupid human, you want me to go to this IP address? Great, let me get the MAC address. ARP will do that. Hey, who's got 134.241.100.1? Right? The answer should come back. Switches operate at layer 1. Oh, by the way, hubs operate at layer 1. Switches operate at layer 2. A switch actually picks up off the wire, reads the destination MAC, the source MAC, puts it in a table so that way it knows for routing information, does some layer 2 routing, if you will, and it only puts it down the wire. So if I'm sitting there saying, hey, I want to go to the workstation that's on port 3, only port 3 will get the traffic. Meanwhile, a stupid hub just takes electronic signals off a wire and pushes it down it's just a repeater, right? If it has 8 ports, all 8 ports gets, all 7 ports get what port 1 sends down the tube, okay? So switches operate at layer 2. At layer 3, we have our IP addresses. We have V4, which is 32 bits. It's written decimal, so 10.10.10.10. Right? It's going to have that format. Okay. IPv6 has 128 bits. It came out because IPv4 has run out of addresses, although we're making it work thanks to NAT. So both these IP addresses are going to have a host address and a network address, right? The host address is that workstation specific on its subnet, and the network address is the subnet, right? Think of when you write your home address, right? You have, I'm going to give my address when I was a little boy going off to grade school. I was 52 Portulaca, right? That is my host address. That's the house actual address, right? If I'm standing on Peekskill or Wilbraham Road and someone says, hey kid, where do you live? I would just say 52 Portulaca, right? And they would know I'm already in that neighborhood. They know in that neighborhood I'm on that house. However, if someone asks me in California, I'm walking around California, hey kid, what's your address? I'm going to say 52 Portulaca, which is my house address. Springfield, Mass. 01129, right? That was my network address. That's the subnet I live on. Okay, that's one way to look at it. Routers live on layer 3. They're going to move us from one subnet to another subnet with the eventual goal to end up on the subnet we want to get to, right? So it works on 2 layers. It's going to move traffic from one subnet to another subnet, one interface to another interface. A router has at least 2 interfaces, either logically, which we'll talk about in this class, or physically. But we're going to move traffic from one interface to another interface. And with the eventual goal of getting to wherever the end interface is going to be, right? That could be 20, 30, 50 hops later, okay? 250 hops later, moving from subnet to subnet. 250 subnets later, we finally get to the subnet we want to get to. That happens, okay? So it's responsible for forwarding traffic from one subnet to another. There's static routing versus dynamic routing. We're going to get into that, but static routing is programmed in by the human. Dynamic routing is learned by the router, right? It's going to talk a routing language, RIP. We'll learn RIP. We're going to learn OSPF, EIGRP, and there's one OSPF, EIGRP, RIP. Those are we're going to certainly learn those 3, and those are routing languages, and routers can talk to other routers and advertise routes and advertise networks. Okay, and then when they learn those routes, those are dynamic routes. Static routes are the human types it in manually. Okay, some background cello music, shall we? All right. Let's talk about IPv6 real quick. Again, IPv4 we have a sliding scale, which we'll talk about where the host is and where the network is. IPv6 it's locked in stone. The first 64 bits is the network. What it does is it takes the MAC address, which is 48 bits, and then it adds 18 to the bits. It adds 18 more bits off the MAC address to create the network address, which is kind of smart. And then we have 64 bits. That's the 64 bits to the host. To the 64 bits to the network, that's the network identifier. Okay, some key ones that we might want to memorize. We have the global unicast address. These are globally unique on the internet. We have, which again, that would be for the network portion. By the way, it goes network is first, so the network's on the left, and the host is on the right, just like IPv4. Anything starting with Foxtrot Echoes 80 is going to be a link local address. Anything starting with a Foxtrot 00 will be a multicast address, and any cast will. There's a way in IPv6 to share addresses essentially. So, all right, notation. First, you can drop any leading zeros in each of the individual blocks, and then replace the biggest continuous block of zeros with a double colon. Right. So, in this case, we have 2001 0. Why not? This is 0, not an O, because it's hexadecimal, so there is no O. It's just a 0. So 0 Delta Bravo 8 3 Charlie 4 Delta 0012. 8 zeros in a row. Well, that's a prime target. 1, 2, 3, 4, 5, 6 Alpha Bravo, right? So that address becomes 2001. Why can't I drop these zeros? Because they're not leading zeros, right? We can drop leading zeros, right? So we got 2001. We can drop this leading zero, right? We can drop it free of charge, right? The computer can figure it out. If it just sees 3 characters in the middle, it's going to say, oh, there's a leading zero, and I can just pop that in, right? And there's only apparently 1, because I know there's supposed to be 4 characters in there, right? 3 Charlie 4 Delta, right? Now we drop those 2 leading zeros. Again, the computer says, wait, there's only 2 characters here. There's supposed to be 4, so therefore there's 2 leading zeros, right? Now it can only do this trick once, only once. Right, only once. The biggest contiguous block of zeros, I can condense it down to a double colon. Okay, I can only do that once, because if I did it multiple times, the computer wouldn't know which one is 2 blocks and the other one's 1 block, right? So there you go. So I take all 8 zeros, I double colon it, and then 1, 2, 3, 4, 5, 6 Alpha Bravo does not have any leading zeros, so I don't leave it. All right. Again, what we do is for the host address, we take the MAC address and we have a process which we can then reverse engineer. So therefore, we don't need ARP and we don't need as many broadcasts in IPv6, making IPv6 better. We also don't need NAT. So that NAT, in theory, IPv6 should be faster, better, stronger. It is kind of more innovative. It's smarter. We ignore it. Okay. So it's there's less need for broadcasts. Also, DHCP can work without broadcast because the router advertises its network. So therefore, I don't need to ask for an address because I have it. It's just my MAC address going through that process. It's auto-configured. It still does need DNS. Actually, it needs DNS almost more. It's hard to memorize an IPv6 address. ICMP is integrated into it. Multicast has better integration. There's no need for NAT. I said that. So why is IPv still around and more popular? Well, it's around. We do have this thing called dual stacking, where a lot of networks, stick included, has IPv4 and IPv6 running at the same time. We can do tunneling, so that means we can have one part of our journey go IPv6, tunnel it through an IPv4 network, and then have it end up at an IPv6 network on the other side. Right? There's a couple different strategies that we can have them work side by side. Some would say we're doing a slow migration. Some would say we're having a stalled migration. Why aren't we at IPv6? That's a long story topic. So, that being said, let's learn. And now I'm going to force you to learn the old way, because I swear it's so there. Again, layer 3 IPv4. We have classes. Class A, the first bit's going to be a 0. That means networks 1 through 127. We have the private IP. Remember, because we need NAT so much because we're out of IP addresses. We have private addresses. The private address space on Class A is 10. The first bits on a class B are 10, so therefore that's going to be networks 128 through 191. There's no other way. If that's the pattern, the first two bits are going to be 1 and 0. There's no way to get to any other IP. So the first octet is going to be 128 to 191. The private address space there is 172.16.0.0.12. Because it's a /12, that means it goes from 16 to brain not working 128, 64, 32, 16. So it's a 16 address space. So therefore it's going to go from 172 to 16 to 172 to 32. All right. Class C, the first three bits are going to be 1 and 0. Therefore, it's 192 to 223. The private address space there is the very popular 192.168.0.0/16. These last two are manipulable. D is for multicast. Do not use it. It's not meant for individual workstations. And E is for experimentation. You can use it with Linux boxes. That's not recommended because some devices won't like it very much. Windows will not take it at all. So there, as far as I know, there's probably a driver upgrade or driver hack you can do to it, but you can get square peg round hole, but you have to do some shaving. All right, we have classful. We're going to talk about this with RIP in this class. So if we're talking about a classful protocol, that means it's going to assume if it sees a network of 17.8.5.4, it's going to assume the 17 is the network portion and the last three octets is the host portion. That's what we mean by classful, right? Class A is going to be 8 bits, Class B is going to be 16 bits, and Class C is going to be 24 bits CIDR. Okay, CIDR, VLSM, oh no, not this crap again. Yes, this crap again. I do have a link here to our now famous practice site. Again, 130, 194, real quick, I'll do this one. Let's bring it over here. I can't copy and paste easily. Let me zoom in so you can see it better. That's awesome. And then we're going to go shift window down. I got 131. Well, I don't really care about these two bits. So remember, can I draw on this? I cannot, I don't think. So let's 130, 194, 90, 137. Let's see how good my memory is. So I'm going to shift down to my sketch pad. Was it 134? Already I forgot. It was 130 dots. Let's go back up. I can just do that. 130, 194, 90. 194.90. This is exciting video, I know. 137. All right, and it was a /21. I'll verify that because I just want to make sure I get it right and not find out later. /21. All right. Because I have a /21, what does that mean? Well, this octet is locked in stone. This octet is locked in stone because that's 8 bits. That's 8 bits, right? This octet right here, 16. We have 5 hangers over. What's the 5 hangers over mean? Well, 128, 64, 32, 16, 8, 4, 2, 1, right? 1, 2, 3, 4, 5. It means my networks are going to increment by 8, right? So 134.194.80.0 is a network. 88 is a network. Whoa. Therefore, 96 is a network. 88, 96, that means I am on the 88 network, right? So my network there is going to be 130. That just gets dropped down. 194, great. 88, I believe I said. .0. Why is it .0? Because we're going to zero out the whole host portion. Remember, that means the host portion here is going to be these 3 bits and then this 8 bits here. So 11 bits, which makes sense. 11 plus 21 is 32. There's 32 total bits. These 11 bits are the host portion. These 21 bits, it's right there in my face, are the network address, right? So we have 88.0 is going to be the network. The first host, therefore, is going to be, just click it up 1, right? And that's a legitimate host address, right? The last host address is going to be a little tricky, right? Because we have to go for the broadcast. Now remember, the network range is 88 all the way to 96 because my increment is 8, right? If my increment is 8 and 96 is my next network, that means I got to click it back 1, 95, right? 255 would be my broadcast, because if I click it back one, that's the broadcast. 254. All right, and then finally the broadcast is going to be 95.255. So I said 88.0, 88.1, 95, 254, 95, 255. Let's see if I know what I'm talking about. Show all. Yeah, I think I just do show. So we got 88.0, 88.1, 95, 254, 95.255. Okay. Again, practice. Let's do this one. All right, so this is easy. /16. So the first locked. This is 1 bit. So if I have 1 bit, that means my increment's 128. So my first network's going to be 0, 0. So or 0. And this is therefore going to get dragged into a 0. So 131.58.0. First one will be 131.58.0.1. The last address would be, I got to go all the way to the next network, which is 128. Go back one. That'll be 127. And this would be its last host, so 254. 127, 254. And then this one would be 127, 255. All right? Practice. And then eventually it'll make sense. So remember, we have broadcast address. We talked about that. That's when the host portion is all ones. That means everyone in the whole subnet hears it. It's a broadcast to everyone. We have multicast, which is kind of like a broadcast, but it goes out to multiple subnets. We're going to talk about that because routing protocols use multicast, right? We need to send out messages to multiple subnets. Therefore, multicast will work well. IP headers. Remember, our IP packet is going to look like. Shift window down. I'll clear. There's a way to clear. I'll just do property size. I don't want to do that. I'll select everything, and I can delete it. Awesome. Thank you. All right. I'm still learning this tool a little bit. All right, and then we'll go back to pencil. Remember, a packet. We're gonna have. Well, I should just draw one big box. Here we go. Right. When we have a packet, we're going to have a layer 4 header, or a segment, if you will, right? Actually, layer 2. This will be layer 2, which will have the MAC addresses. Layer 3 will have the IP addresses. Also, it's going to have hash values, right? Because if we want to make sure every time we manipulate data, we want to put a hash to make sure we get it right. Then we have our layer 4 header. We're going to have data, Mr. Data. Oh, that's going to be a new series too, right? Picard's coming back. Layer 2, and then we have a layer 2 footer. The layer 2 footer actually has the hash value for layer 2. Layer 2 just has the MAC addresses, right? Source MAC, destination MAC. This is going to have the IP addresses, source IP, destination IP, and this is going to have the port numbers. Okay? So we're going to be able to strip off this data as it comes into our routers, into our switches, and read that data. It's not encrypted. It's not super science. It's fine. Okay? There we go. Remember, layer 4, we have ports. We have divided into 3 categories. Well-known ports are 0 through 1023. Registered ports are 1024 to 49151. Well-known ports are going to be our popular port, FTP, web, port 80, 21, and 20 is FTP. I'm just trying to think of some off the top of my head now. My brain's going belly up on me. Another one we're going to use TFTP, which is port 69 using UDP. So well-known ports, the registered ports, and then we have dynamic ports, which are above 49151, and it's probably actually 49152, going all the way to 65,535. These are going to be randomly assigned, usually. So what we're going to have, if you're, case in point, you right now going to Blackboard, which is actually 443 for SSL traffic at HTTPS, the server you're hitting is going to have 443 as its destination port. The source port is going to be randomly generated because we can keep track with the data. We do care about it, but it doesn't really matter. It doesn't have to be a specific port. We just need to know when we hit the server, hey, I want to talk to your 443, right? That way, because if you have a HTTPS server and an HTTP server, we'll know you're going to the HTTPS server because you're going to 443. Oh, 443, you want my HTTPS page, not my HTTP page, which would be port 80, right? So that helps. Port records are kept by IANA. As I just said right here, this is everything I just said about ports. Okay. Here are some common ports that I would recommend you memorize. SSH was 22, and that's why I wanted. Telnet 23. My brain was fighting over that for some stupid reason. So, anyway, there we go. These are ports that you should memorize. So. And then 5 through 7, we have modern firewalls that use a heuristic approach. They do pattern searching. We can look at application data. Remember that just again going back to Mr. Data. We can look into this too, if it's not encrypted, right? We can look into this data. Sometimes nowadays with HTTPS, for example, that would be encrypted data, and we'd have a hard time. We just go, I don't know what it is, but we know it's encrypted because we don't know what it is, right? So we can do some data information on that. Remember, applications, FTP was for file transfer. FTP is trivial file transfer. We're going to get some of that here in the wonderful world of Cisco. Telnet, SSH, HTTP. All right. All right, some features which we're going to talk about in this class. Network address translation. We are going to get deep on that. So we're going to do single NATs where we just translate a single IP into a single IP. We're going to do port address translation when we have multiple IPs that we're going to translate into a single IP. VLANs, we're going to jump right into that as well. Remember with VLANs, we can have VLAN tagging. So what we're going to do is we're going to put a little extra port right there. That's going to have the VLAN ID, right? VLAN ID. And it's just going to be a little number in there. 2. I'm on VLAN 2, right? And so with our switches that take that off a trunk port, we then know that is meant for VLAN 2, a virtual subnet, right? So that way we can have a switch that does VLANs, even though it has it's a switch. It can divide itself up into like 5, 6, 100, 1,000 multiple switches, right? Because every single port could be on its own virtual subnet, right? So that's what a VLAN is. And we're going to have access port and trunk ports. Trunk ports carry multiple VLANs. Access ports only carry one VLAN. All right. Access control lists, we'll talk about those. That's going to deny or allow traffic based off its IP address or its port or its MAC address. Actually, also there are ACLs that use MAC addresses. Firewalls have multiple generations. We're not going to get too in depth in firewalls in this class. That's going to be a security class. Intrusion detection system, intrusion prevention. That's going to scan data, looking for nasty traffic. ICMP will do a lot of that. Internet control messaging protocol, management protocol. My brain's not working right now. Anyway, that protocol will, the ICMP protocol is what lets us ping. We're going to have ICMP echo request. Let's see what it stands for. What do you mean it can't be reached? Oh, I put a slash in there by accident. All right, Internet Control Message Protocol. Again, the first answer is usually the right answer. All right, so ICMP, it's going to allow us ping. We can also do things like trace route, and but it allows us to do some testing on the network. And then we're going to talk about simple network messaging protocol. That's right where my brain was frying. And syslogs, right? Cisco and Cisco World, we're going to use both of these. We're going to use traps, and we're going to use syslog to send messages to log things, which is important. All right, so in summary, there are multiple network models. We have the OSI, DoD, TCP/IP. Network models are good for troubleshooting, right? You're going to sit there and say, wait, what layer is this? You could look at a problem and say, wait, I'm not even able to get a hold of another workstation on my subnet. Never mind the internet. This isn't a layer 3 issue. This is a layer 2 issue, right? So let's figure out what's going on. All right. You need to know the various medias to transmit data. Collisions can happen at the first layer. Switches operate in the second layer and break up collision domains. We didn't really talk about collision domains, but a switch breaks up a collision domain because you can't. It's really, really, really difficult to have a collision when you have two networks on the same collision domain, right? And a switch, because they pick it up and put it down off the wire, it does carry a sense media access collision detection, collision avoidance if it's an access point. And therefore, it's going to be really hard. It's like having two cars on a road. The chances of them hitting each other are very rare. Okay, insert joke about your not driving well relative. All right, routers and logical addresses operate at layer 3. IPv4s run out of addresses. IPv6 is overdue. It does not like my spelling of overdue. Put it together. Overdue to replace IPv4. Ports at layer 4 allow computers to know what application is communicating. Talking about cars, I'm thinking of commuting. All right, that's just kind of our refresher. I know I went through fast, but again, Networks 1, Networks 2 should have been really hammering this stuff home in your head. Again, practice on the VLSM. I'm just going to assume you know how to do any of this and all this and have an understanding. If you need further instruction, you need me to go over something in more detail, let me know. I can do that during my office hours or some other time if we work it out ahead of time. All right, thank you. I'll talk to you later. Bye.